to the second part of Lecture 9. In this one, we will get acquainted with the mesmerizing phenomenon of gravitational lensing. Gravitational lensing is the fact that according to general relativity, gravity can bend light. So according to Newtonian gravity, of course, the gravity depends on the mass of both the objects that are influencing each other. But according to Einsteinian gravity, gravity basically bends the geometry of space-time. And once that geometry of space-time is bent, even massless particles such as photons will follow these like bent curves on their path through the cosmos. And so Einstein predicted back in his day that it would be possible to see lights distorted simply by gravity. But he also predicted that this effect would be so weak and so faint that we would never actually be able to observe it in practice. Today, we observe it more or less routinely, and it is nothing less than absolutely stunning. So let's take a look at a few basic and idealized concepts of gravitational lensing. Let's start out by looking at this figure over here. This is a simplified schematic of a system where we have an observer here. We have a lens somewhere here. This lens can have some kind of extent. And then we have a background source somewhere over here on this thing we call the source plane. And so in this setup, we also have these three different distances: the distance from the observer to the lens, from the lens to the source, and from the observer to the source. And we define some angles, of which I suppose this one is the most important. This is called the deflection angle, and it is the difference, the angle between the angular position between the lens and the source in reality, and its apparent position as a result of the lensing. So we start out by defining the source plane and the lens plane. The source plane is basically a plane, like both physically and mathematically speaking, a plane which is perpendicular to the line between the observer and the lens, and at the same distance as a background source. And then we have the lens plane, and of course that is the same thing, except it is at the distance of the lens. And what is important here is that even though the lens has some kind of extent in this direction here, this is usually quite small compared to the overall distances that we're looking at. So we're working with this thing that we call the flat lens approximation, basically assuming that the lens is a two-dimensional object that sits here. This saves us a lot of computations that end up not really being that important in the end. Anyway, they don't really change the result much. So that is what everybody works with. And then we have this strange thing here called the image plane. And unlike the two others, the image plane is not a physical plane as much as it is it's a mathematical plane. If we think of the source plane as this plane where we have the source, obviously, and the lens plane as some kind of operator, then the image plane is the result of the lensing operation on the source plane, and it is the plane, the apparent plane that we see, that we observe. So it is the apparent location and the apparent shape of the lensed object as it looks to us, unlike the source plane, which is the true location and the true shape of the lensed object. And the lens plane is the plane of, again, the lensing object itself. And in the special case where the source and the lens and the observer are lining up directly behind each other, and the source and the lens can be approximated reasonably well with a point mass, then we get this curious case where the light can equally well be directed in this direction here, or be bent in this direction here, or in other directions as well. So what we will see is that if it is a point source, we will see a so-called Einstein cross, where we basically see 4 images of the source around a circle, or we will see a so-called Einstein ring for an extended source rather than a point source. An example of such an Einstein ring is this object here called SPT 0418, which is observed by the templates team by using JWST. This is a particularly beautiful example of an Einstein ring. You can actually see it as both an Einstein ring and a cross, right? You can see that there is this cross formed by these 4 parts here, which is like the main luminous core of the background galaxy, and then it also has like a more extended component which reaches around and forms an Einstein ring. So this is a very rare case and a very cool case where the observer, the lens, and the background object are almost perfectly aligned, and also where the lens itself is an almost perfectly spherical galaxy itself. Oftentimes, though, the situation is a good deal more messy than that. For example, often the lensing object is not a single galaxy, but a galaxy cluster, which has an overall dark matter distribution that is rather smooth. But on top of that, each galaxy in the cluster also has its own dark matter halo. So that is like a hierarchy of halos on top of halos, and it gives a very messy lensing potential, and as one can imagine, therefore also quite messy lensed images. For example, we can take a look at this quite famous object here called the cosmic snake. It is a rather old observation, but we can see that here we have an image of the galaxy, and here we have another gravitational lensed image of the galaxy. And we can see that it is following rather smoothly the curvature of the dark matter halo of the galaxy cluster. But once it gets close to individual cluster member galaxy, it also gets perturbed by them. So we see this kind of a wobbling pattern that we see here. It's a very cool image, I think. It's really fascinating, but it also goes to show that this lensing image or this lensing business can be quite messy sometimes. The effect of lensing, because it is so messy, we cannot really describe it like mathematically in a perfect way. So what we usually do is that we describe it in terms of differentials, right? So in this case, we will look at what we call the convergence and the shear of this lensing potential. This is like the effect of lensing can be described using this line of sight projected gravitational potential, and to the first order, it can be quantified into the convergence and the shear. And basically, the convergence is a matter of the magnification, and the shear affects the stretching and distortion of the image, but not its size. You can see how the magnification is and the shear are mathematically expressed over here. So this is the convergence at a given point in 2D space, right? So you can see that these two coordinates here are basically the projected angular coordinates of the deflection, as we saw before in here, right? This is the vector theta. And these are the two main two-dimensional coordinates of this deflection angle. And it is given by this thing phi, which is again given by this thing here, which the more important thing is, well, it's given by the surface density at this given point, and then divided by what we call the critical density. And the critical density is an extremely important concept in gravitational lensing that we will get back to later. Here is the definition of these psi ij. Here's not phi. I'm sorry for my wrong Greek. It is psi. And psi ij is given as these differentials here, where phi itself is basically, it's called the reduced, the lensing potential, the reduced lensing potential. It is proportional to the actual projected lensing potential. The convergence are where these are the doubly differentiated in the same direction, and here the shear are the mixed differentials of this reduced potential. So basically, what we can learn from this, right, is that the shear and the convergence depend basically only on the steepness and the direction of the gravitational potential of the lensing system at a given projected two-dimensional angle. And then we have this thing here called the critical density, which is given by this thing here. We don't need to think too much about that. The important part is that the critical density is such that if we have a density that is above, and again, this is a density of the lens, right? Sorry, this is a density of the lens, not of the source. But on places of the lens where we have a density that is above the critical density, we will see multiple images of the background source. And if we don't have anywhere where the density is above the critical density, we will not see multiple images of the background source. So lensing comes because the differences in the strengths of the shear and the convergence, and because of how they depend on the steepness and direction of the slope of the gravitational potential in the lens, it means, of course, that lensing can come in different degrees of strength. And the first one, strong lensing, is exactly when the density, the surface density, surpasses the critical density. At this point, we will get multiple images. We will get significant convergence, means that we will get actual magnification of the background source. And we will also sometimes, but not always, get a very, very significant share of in the images that we see of the background source. And this effect is very useful often as what we would call like a cosmic telescope. This is actually something I use a lot in my own personal research. So that's something that's kind of close to my heart. It is sometimes indeed very useful for that. And then we have what we call weak lensing. That is when the surface density is below the critical density everywhere, or where it is below the critical density. In this case, we get single imaging, we get weak convergence, or sometimes no convergence at all, or close to no convergence at all at least. But we can use statistical maps of the shear to find out the projected mass of the lens system, the mass density of the lens system. Remember back when I talked about the bullet cluster a couple of lectures back, and I showed how you could show that the hot X-ray gas, which was supposed to make up like 90% of the baryonic mass of these clusters, was in one location, And then using gravitational lensing, you could map that the actual like gravitational lensing determined mass of these two clusters were in completely different places, which was a very, very strong argument for dark matter existing, because clearly the effects of the mass were localized somewhere completely else than where the majority of the baryonic mass was located. Anyway, that makes weak lensing extremely useful for mapping masses at large scales where we don't really have any other ways of mapping this mass, simply because there isn't always luminous mass available for us to use to map this mass. Also, it provides an independent measure of these mass distributions that we can use in tandem or like in concert with, for example, hot X-ray gas or stellar dynamics, as multiple independent ways of determining a mass distribution, which, if they converge, can tell us that we probably have a pretty good measurement of this. And if they don't, they can show us that we are probably doing something less than optimally, and we need to work more on it before we can believe the masses that we get out of it. And finally, we also have the phenomenon of microlensing. That is something we don't actually use in this course, and we won't talk more about it. But it is when the lens is a single star or even a single planet. So when things then move past each other, like when things kind of move in front of each other, because you can see the motions of single stars moving in front of each other, then it will, for a short while, it will give this like brief boost of the light of the background source. And it will not be a periodic boost. It will only happen once. So this can be used to, for example, search for exoplanets or for stellar mass black holes or many other things like that. So it's quite useful, it's quite interesting, but it is not super useful in the research of galaxies. So we will not be thinking more about it in this course. This was the end of part B. Again, thank you for staying with me this long. This was a rather large one as well. I will see you in the next one. Bye for now.